As they try to unravel the mysteries of the universe, scientists are coming to an astounding conclusion. To make sense of outer space, they need to understand inner space, the microscopic matter that forms the foundation of everything we see. But shrinking down billions of times into the realm of atoms and subatomic particles takes us into a strange, unexplored world.
When we descend into the microscopic world, we find that it's really weird and indeed downright bizarre and unbelievable.
The stuff in this universe is far smaller than anything we can see with a microscope, but it holds the key to the cosmos.
We can only understand where we came from if we understand this crazy micro world.
So let's go on a fantastic voyage into an uncharted world known as the microscopic universe. When people talk about the universe, they usually mean the vast expanse of space, billions of light years across, that they can see with radio telescopes and cosmic imaging.
They think about stars and galaxies and planets and all the big stuff out there.
You have astronomical bodies moving under the force of gravity.
There are laws of nature, and you think that the laws are right once and for all.
However, there is another universe, an unseen world that governs everything we see.
When we go down in size, trillions of times smaller, to the microscopic world, the rules are much less intuitive than the ones we're used to from the large-scale world.
The magic of the microscopic universe begins at about a 10/1000th of a meter, or the size of an atom. Matter behaves so differently at this level that scientists have developed an entirely new set of rules to describe what's going on. They call it quantum theory, and what it says is extraordinary.
This baseball represents a subatomic particle, like an electron or a photon of light, that routinely does all sorts of weird, strange things in the microscopic universe. The subatomic version of this baseball can be invisible, can go through solid objects with ease, can be in multiple places at the same time, and can seemingly go backwards in time and change the past. This means I could throw this microscopic baseball to first base and to home plate at the same time, or change the seemingly predetermined outcome of a play while it's still going on. Now, this is the stuff of science fiction, but really, we know it to be true, or at least it appears to be true in our quantum world. We get all sorts of weird things happening.
If scientists can understand how these weird things work, they'll be able to put them to use in our everyday world, revolutionizing modern computing and perhaps even allowing us to communicate across the cosmos instantly. The key to making these miracles come true is a process called quantum entanglement, and scientists are already harnessing this astounding discovery for both civilian and military purposes.
In quantum physics, what happens to an object over here can instantly affect an object over here, and over here could be millions of miles away.
This is how it works. When two subatomic particles interact, they can become entangled. That means their spin, position, or other properties become linked through a process unknown to modern science.
If you then make a measurement of one of the particles, then that instantaneously determines what the behavior of the other particle should be. And when the experiment is done, it's found that indeed the other particle's quantum state is exactly determined once you've made a measurement of the partner particle's quantum state.
That means if a scientist observes one entangled particle and forces it to spin clockwise, the other entangled particle will immediately start spinning in the opposite direction. That seems intriguing, but it's hardly earth-shattering until you consider that the two entangled particles can be separated by billions of light years. And still, the moment you observe one particle's spin, you've dictated the other particle's spin.
That's weird because it may suggest that information has traveled instantaneously, faster than the speed of light, from one particle to another. I don't understand it. I don't know that anyone does. Spooky action at a distance, as Einstein called it.
Quantum entanglement is more than a curiosity of the microscopic world, because the effects of entangled particles can be seen and felt in our world. If scientists can overcome some fundamental obstacles, quantum entanglement could someday help humans communicate across vast distances instantly.
People sometimes think that quantum entanglement will achieve the desired goal of transferring information at a speed faster than that of light. I don't think this will be achieved because to set up these systems, you had to have brought them there at speeds slower than the speed of light. But then what do I know? 100 years ago, they didn't think that we'd be going to the moon.
Quantum entanglement is far more likely to transform modern computing. Scientists hope to use the magic of the microscopic universe to build powerful new computers.
We're going to see what this baby can do.
At the Massachusetts Institute of Technology, Professor Seth Lloyd has helped create a prototype of a quantum computer which uses quantum bits rather than traditional computer bits to perform its calculations.
This lab has the world's best superconducting quantum bit, or qubit, in it. And when we do quantum computations with qubits, we can have the quantum computer do multiple tasks simultaneously. It can do this, it can do that at the same time. It can add 2 plus 2, it can add 1 plus 3, and it can add those two things simultaneously.
The fact that a single qubit can perform many calculations at the same time gives the quantum computer the potential to be far more powerful than any computer ever imagined. Like traditional computers in the 1950s, quantum computers are in their infancy today. The machines take up large rooms and can do only the most basic calculations. But they hold great promise for the future.
Quantum physics is notoriously weird, strange, and counterintuitive. And so quantum computers use this weirdness to compute in ways that classical computers can't.
The major stumbling block is figuring out how to effectively code classical information, the ones and zeros that computers use, in a way the microscopic universe can process it using entangled particles. But when scientists figure that out, quantum computers could transform the planet.
Even if you have a quantum computer with not that very many bits, you might still be able to do things like break all the codes that people use to communicate on the internet. Or you could solve very difficult problems having gajillions of variables, like try to figure out what happened at the Big Bang.
That may be hard to believe, but the microscopic universe gets even stranger. In fact, the most famous experiment in quantum physics shows how one object can be in two places at the same time. A result that startled the great Albert Einstein. As scientists explore the microscopic universe, they find it's governed by rules that are often incomprehensible to those of us in the normal world. At the smallest scales imaginable, not only does information appear to travel faster than the speed of light, But human observation often seems to decide what happens.
It seems like the behavior of quantum mechanical stuff is different when we're looking at it than when we're not looking at it.
This profound conclusion comes from performing the double hole experiment. Scientists first conducted this experiment a century ago, firing photons of light through a metal plate with two slits. The light that went through the holes hit a screen behind the plate.
I'm going to demonstrate the results of this amazing experiment with a bunch of baseballs and a barrier that we've set up which has two holes in it. Now, normally in the everyday world, if I throw baseballs through one hole or the other, they'll form a predictable pattern on a screen that we've set up behind home plate. They'll be in one place or the other. Now, let's make that pattern with a whole bunch of baseballs. I'm going to use this pitching machine. Here's the first one. Let's see what happens. Now you see, the balls landed on the screen in two bunches, pretty much along a direct line from each of the two holes. That's natural. That's what we expect. But when we descend into the microscopic universe and use electrons, which are 10 trillion times smaller than baseballs, we get a very different, odd result when we perform this experiment. A pattern that you would expect if these were waves going through both holes at the same time and interfering with themselves. Well, we usually think of electrons as being particles, so how can they exhibit wave-like properties?
These test results were confounding. The electron was a particle before it was fired at the screen, yet it formed a pattern on the screen, as if this single electron had gone through both holes at the same time. Does a microscopic particle spontaneously clone itself in midair? After years of study, scientists still don't know exactly what's happening.
Probably the most magical thing is that in quantum physics, an object can be in more than one place at the same time.
It actually can sense both slits and actually go through and quantum mechanically feel the structure of both slits in the experiment.
Most physicists agree that the math is quite solid and leads to solutions that are undeniable and can be confirmed with experimental measurements. But exactly what is happening and how is a matter of debate.
To try to grasp this amazing experimental result, scientists decided to observe how individual electrons behaved when they went through the double slit. How exactly could a particle go through both holes at the same time?
Scientists got a front row seat to observe the strange behavior of these electrons or other subatomic particles or even photons of light. Doesn't really matter as long as they're small. They didn't just look at where they landed on the screen back there. They also watched the behavior of the particles as they went through the holes. And then they saw something amazing. When scientists were watching the holes, the electrons behaved like particles, forming the baseball-like pattern on the screen back there. But when the scientists weren't watching, then the electrons behaved like waves. They formed a pattern that looked like the interference pattern produced by waves on a screen. That's really strange. What you see depends on whether you're watching or not. If you're watching, you see the particle-like behavior, like baseballs. If you're not watching, you see a wave-like behavior, but not both at the same time.
This was nothing less than astounding. Observation seems to change the nature of subatomic particles.
Mysteriously, when we're not looking, things are waves. When we are looking, they look like particles. So even an electron, which seems to us like a particle, has wave-like properties when we're not looking at it.
The fact that when we don't look, the electron appears to go through both holes, but when we do look, we always see it go through one hole or the other, is what we call the quantum enigma.
How could our decision about whether to observe something change how that something acts? There is a technical explanation.
To make an observation, you somehow have to interact with the system. For example, you have to shine light on it, which then bounces off and you observe the light. That's how we can tell that a baseball is here or there. We bounce light off of it. Well, for macroscopic particles, that doesn't disturb them very much. But for microscopic particles, the act of bouncing the light off of the particle changes where it is and how it's moving.
So in the microscopic universe, where photons of light are about the same size as subatomic particles, these photons have a big impact when they illuminate the particles so we can see them. But this doesn't answer the question. Why doesn't the light simply change the direction of the subatomic particles? Why does observation actually change the nature of what is being observed?
The short answer is we don't know. This is the fundamental mystery of quantum mechanics, the reason why quantum mechanics is difficult. Mysteriously, when we look at things, we see particles. That when we're not looking, things are waves.
This is something we scientists have argued passionately about now for almost 100 years, and there's still no consensus.
When they were first released a century ago, these test results were enough to unsettle the brightest mind in science.
Einstein said, "I don't believe in quantum physics because I believe the moon is there even when I'm not looking at it." Einstein was, of course, referring to the implications of the theory that the moon really isn't anywhere until it's observed.
However, the double hole experiment's mind-boggling conclusions don't end there. In recent years, technology has allowed scientists to perform a fascinating variation of the test. Its results call into question our perception of time itself.
This is like a high-tech version of the double hole experiment. Electrons are being fired toward a barrier with two holes in it. But the scientists can delay their decision about whether to observe the electrons until after they've passed through the holes, but before they hit the screen. It's as though I'm on a baseball field, and there's a baseball being pitched toward the barrier with the holes in it. But my eyes are closed, so it goes through, and it behaves like a wave, but then at the last second before it hits the screen, I open my eyes and decide to observe it.
At that moment, the electrons, in essence, become particles, and seemingly always were particles from the time they left the electron gun.
So it's as though they went back in time to before they went through the holes and decided to go through one or the other, not through both as they would have had they been behaving like waves. That's really crazy.
That's the enigma. That our choice of what experiment to do determines the prior state of the electron. Somehow or other, we've had an influence on it which appears to travel backwards in time.
Scientists are only beginning to grasp what these microscopic mysteries mean for time travel and changing the past in our everyday world. But one thing is clear. The rules that govern this subatomic world hint at a universe that's just as mysterious as science fiction. In fact, quantum physics may suggest that reality is simply a figment of our imagination. After discovering mysteries in the microscopic universe, scientists wanted to quickly unravel, study, and solve them. But as they tried to figure out exactly what was going on in this strange subatomic realm, they found something completely unexpected. Nature refused to tell them.
When we descend into the microscopic world, we find that there's a fundamental uncertainty in essentially all quantities that we wish to measure. And it's not a problem with the measurement process. It's that nature herself does not know.
Scientists call this the uncertainty principle, and as strange as it is, it may be the most profound concept to emerge from the microscopic universe. We simply cannot know anything with absolute certainty.
In our everyday world, we think we know a lot about the things around us. We can actually locate, for example, the position of this cue ball and strike it at a certain speed, which we know, and we can use that to collide it into other balls and go ahead and play a game of pool. But what actually happens if we shrink everything down trillions of times? In that world, these pool balls are now actually like subatomic particles.
In this microscopic realm, quantum physicists have found they simply cannot determine with any precision where these particles are located because of their wave-like qualities. And what's even stranger, if scientists try to box in a particle, it will always generate enough energy to break out of the box before its position and speed have been determined. The uncertainty principle says nature will not allow its fundamental elements to be boxed in.
So because in the microscopic world, because particles will interact with a completely different set of rules, the rules of quantum physics, a microscopic pool will be a completely different game.
The uncertainty of the microscopic universe extends far beyond the location of particles. It applies to everything, including a particle's energy, and this gives rise to a stunning phenomenon called quantum tunneling.
In classical physics, if you throw a ball at a wall and you don't throw it hard enough, it won't go through the wall, it'll bounce back. But if it's an electron and you don't throw it hard enough to go through the wall, it might go through anyway. We call that quantum tunneling.
How can this be possible? It may sound bizarre, but one way to explain quantum tunneling is that the uncertainty of the microscopic universe allows a particle to borrow energy from the future to breach the barrier and then pay it back after it gets to the other side.
The electron actually already is on the other side of the wall, and therefore it can go through it and appear on the other side of the wall.
Ever since these wonders of the microscopic world were discovered a century ago, people have asked if quantum tunneling, being in multiple places at the same time, and what appears to be traveling backwards in time, can be achieved in our everyday world. Some scientists say we'll never be able to throw a baseball through a solid barrier.
A baseball is a huge number of particles. You would need all of them to collectively suddenly appear in another place for the baseball as a whole to appear in another place. And that's just extraordinarily unlikely. A single electron or a single proton can do this. But the bigger your particle, or the bigger the collection of particles, the more difficult that process of tunneling is.
However, a growing number of physicists are developing a more outrageous theory for what's going on.
We know that these tiny particles can be in two places at the same time. But hey, I'm made of these kinds of particles. So if they can be in two places at once, so can I.
Scientists call this the many worlds interpretation of quantum physics. They say just like the electron in the double hole experiment, human beings are all in multiple places at the same time. They say anytime anyone makes a decision, we don't actually choose one option over another. Instead, we do them both, in slightly different versions of reality.
What happens when you use your mind and your will to decide things is you end up actually making many choices at once, and all of them become realized in different parallel universes.
The many worlds hypothesis of quantum physics says that when I throw a curveball, I do so only in this universe. In another universe, I might be throwing a fastball. And in still another one, I throw a knuckleball for the first time in my life. And in yet another universe, I heave this ball to the outfield. In the many worlds hypothesis, all of these choices are outcomes that occur in universes that are parallel to our own. Just not in ours, but in parallel universes. That's what the many worlds hypothesis tells us.
This may sound far-fetched, but an impressive array of theoretical physicists believe it's the way the microscopic world works. If it's true, the implications of this startling theory go far beyond the baseball diamond. In essence, it suggests there are universes parallel to our own in which the Nazis won World War II. And in another, the American government foiled the 9/11 hijackers. So the World Trade Center still stands in Manhattan.
If you take quantum mechanics absolutely at face value, it says that every time you observe something quantum mechanical, you become two different copies of yourself. There's the copy that got one answer and a copy that got another answer. It just implies there's a huge number of other copies of you that saw slightly different things happen in the universe.
These days, it's completely accepted that the microworld is weird. Many people had hoped that this weirdness could be confined to the microworld, so that big things like us would be immune to it and always be in a single place. But it's become clear now that that hope was naive. The weirdness can't be confined.
The fascinating debate about the many worlds interpretation of quantum physics will rage until physicists finally solve the mysteries of the microscopic universe. However, some astronomers are concluding that we will never be able to fully explain any of these mysteries because, according to their calculations, the vast majority of matter holding the universe together exists in a higher dimension that we can never explore. If there's anything in the microscopic universe stranger than quantum particles, it's the mysterious matter that scientists have never seen, but that plays a crucial role in the formation of planets, solar systems, and galaxies.
Astronomers know that there's all sorts of matter out there that exerts a gravitational influence, but that we can't see. We call that dark matter.
I wouldn't exist if they weren't for dark matter, because dark matter has this nurturing force of bringing things together to form structure, to form galaxies, which are absolutely necessary for life.
Dark matter makes up a staggering 85% of the gravitationally attractive stuff in the universe.
If the dark matter is some kind of particle, then typically millions of dark matter particles will pass through me every second.
But even though they know dark matter exists, astronomers have been confounded by a microscopic mystery. What is it? At first, they thought it was ordinary matter that, for some reason, they couldn't see.
But what happened was astronomers went and took an inventory. We know how much ordinary matter there is in the universe. By ordinary matter, we basically mean atoms, things that are made out of protons, neutrons, and electrons, the elementary particles that go into making you, me, everything on Earth. And it just doesn't measure up. There's not nearly enough ordinary matter in the universe to make up the total.
This conclusion was bizarre. How could most of the matter in the microscopic universe not be made of protons, neutrons, and electrons?
It's been quite shocking to discover that these atoms actually make up just a small minority of all the stuff in the universe. There's 6 times more of an altogether different substance, which is invisible to us.
It's interesting to think that science has brought us to the point where we realize not only are we not the center of the universe, we're not even made of the same stuff as the universe is made of for the most part. Most of the stuff in the universe is this dark matter, and it's some small particle beyond the reach of our direct detection.
Some theoretical physicists speculated that dark matter might be made of neutrinos, tiny particles 1,000 times smaller than an electron that fit many of the known characteristics of dark matter.
We know neutrinos exist, and they have mass, they contribute weight, so maybe we're done. But now it's turned out that they're not neutrinos.
Most of the dark matter is probably not normal neutrinos because they travel very, very quickly, and they wipe out the formation of what's called large-scale structure, the clumping of material, on the scale of galaxies early in the universe's history. So it would be much harder to produce galaxies if the universe is filled with lots and lots of neutrinos zooming around.
So the dark matter is not ordinary matter, it's not neutrinos, it's some wholly new kind of particle that we haven't detected yet.
It has to be some sort of weird subatomic particle left over from the Big Bang when the universe was very hot and dense. A whole zoo of particles was created. Most of them annihilated or decayed into other particles, but some were left over, and they are what are thought to be the dark matter.
But what could this exotic microscopic particle be? Since it's nothing known to science, astronomers proposed an entirely new particle that embodied all of dark matter's characteristics, and then began searching the universe for it. They call it a WIMP, a weakly interacting massive particle.
One of the problems with the WIMP hypothesis is that we've never actually detected a WIMP in a laboratory.
In fact, there's several experiments going on right this minute to look for WIMPs in underground laboratories, and you'd also like to make them in particle accelerators like the Large Hadron Collider in Geneva. So there's a multi-pronged attack to detect WIMPs directly if they're the right answer.
If scientists find evidence of dark matter, will they also find evidence of another world of dark planets? Dark life forms, and a dark matter table of elements.
I don't think they're like us in that the dark matter particles can form planets and so on, because if they could, then we would expect most of the planets in our solar system to actually be made of dark matter. But I think it's much more likely that the dark sector is many different kind of particles that are much more complex than just one.
However, modern science still has not found evidence of this mysterious microscopic material. And a growing number of scientists argue that's because it's not something else. It's somewhere else, like other dimensions.
People have taken very seriously the idea that the dark matter comes from other dimensions or represents ordinary particles that are actually moving in the other dimensions. The thing about other dimensions are we don't see them, we don't interact with them very strongly, so they're a natural place to put the dark matter.
It's conceivable that the gravitational influence in galaxies and clusters of galaxies that we attribute to dark matter in our own universe is actually caused by concentrations of matter in other dimensions that are felt within our dimensions, but will never be discovered within our dimensions because they're actually somewhere else.
Whatever or wherever it is, many physicists are confident they'll eventually discover a complete solution to the dark matter mystery. Unless, they say, it simply exists at an incredibly small size, far smaller than humans have ever been able to explore. That raises the question, what does exist at the smallest scales of the microscopic universe? That's what viewer Jason L. from Houston, Texas wanted to ask the universe.
Jason, I'm glad you asked that question. The smallest things in the universe are the fundamental subatomic particles, like electrons, or the quarks that make up protons and neutrons, or neutrinos. Now, all these particles are thought to be different vibrational modes of a little tiny entity called a string, a little tiny package of energy. And that, then, is the smallest thing from which everything else is made.
Scientists have just started trying to explore strings and other incredibly small stuff in the microscopic universe. And what they've found offers tantalizing clues to a world beyond. As they delve into smaller and smaller spaces in the microscopic universe, scientists have successfully looked inside atoms. But what exists if we continue our fantastic voyage still deeper into this subatomic netherworld?
Even scales that are smaller than the electron are really a vast unexplored territory, more so than solar systems or galaxies or even the universe. Because we can make observations of planets and stars and galaxies in the universe, but it's hard to conduct experiments that allow us to directly explore tiny scales in time and space.
Essentially, what you need to examine the microscopic world is a sharper and sharper tool, something that actually allows you to distinguish the details down at that very small level.
But as scientists try to probe spaces smaller than the atom, they cannot possibly focus enough light to illuminate them. They need something more powerful.
To look more finely, you need more energy. We can go to incredibly small details using high-energy devices of various kinds. Now, the state of the art are actually particle accelerators. We use elementary particles to actually probe the structure of other elementary particles by colliding them together, letting them interact with each other, and then seeing what comes out at various energy scales. So we can continue this process of examining smaller and smaller distances in space and time by actually going to higher and higher energy with collider experiments.
However, the world's largest particle accelerators have not yet generated enough energy to probe things much smaller than the elementary particles inside atoms. Even so, scientists believe something exists at even smaller scales. At a size so tiny, the human mind cannot possibly comprehend it.
Physicists are now trying to understand what's called the Planck length, 10 to the minus 33 power centimeters. That's 20 factors of 10, 20 orders of magnitude smaller than an electron. Now, an electron is yay big, and I exaggerate a lot. So the Planck length is just almost unimaginably smaller than any objects we can actually measure. Nevertheless, physicists are trying to deal with these scales, and that's what string theory is all about.
String theory says that everything that we think of as a particle is actually a tiny vibrating loop of string. To get an idea of how tiny it is, I have here an eyedropper. We're going to put out 1 drop of water. That has about 1 trillion atoms of hydrogen and oxygen. Now, imagine taking 1 hydrogen atom and blowing it up by 10 billion times. It becomes about ½ a meter across. And you might say, can we now see the individual strings inside that hydrogen atom? But the answer is no. We can continue to make it bigger, make one hydrogen atom the size of the solar system. The strings are still too small to be seen. It's only when we make that atom the size of our observable universe that a string becomes macroscopically large. If one hydrogen atom is as big as the whole observable universe, how big is a string? Only about the size of one of these trees. The amazing thing is that we human beings can even talk sensibly about what exists at this microscopic scale.
Not only can scientists talk sensibly, they've also formulated theories about what happens down there.
This is really one of the holy grails of all of science.
We think that ordinary space and time cease to exist at the Planck length. What we don't know is what takes their place. We need to replace our idea of space itself by something more fundamental. Something that might involve different numbers of dimensions or just a different concept entirely.
One possibility is that space at the Planck length resembles the grid on a football field. The yard lines are the fabric of our universe, and there's simply nothing in between.
It could be that time jumps from one discrete point to another, and there are no steps in between.
Like little quantum mechanical ants could tunnel from one spot on the grid to another spot on the grid without ever going into the intervening space in between. Why? Because there isn't any intervening space in between.
Whatever exists at this incredibly small scale, most scientists believe that the concepts of space and time segue into another kind of universe where shrinking smaller is a meaningless concept.
It could be that time and space are what we call emergent properties of the universe, but that if you go to very small spatial scales or very small intervals of time, the concepts of time and space break down. They don't make sense.
Scientists say the conditions at the Planck length may be very similar to those that existed before the Big Bang, when everything in our universe was probably concentrated in a microscopic pinpoint.
Maybe the same answers to the question about what happens to the universe at the very smallest scales may also be connected to knowing what was the universe like before the Big Bang. Did it just come into being at the Big Bang, or was there something different which then turned into the universe that we're familiar with at the Big Bang? These are all questions we don't know the answer to, but are all connected to the issue of what's going on at the Planck scale.
So you might think that these tiny Planck scale things have nothing to do with us, who are much bigger, but actually it has everything to do with us. It's our origins. Our entire universe, if we extrapolate backwards, would have been smaller than the Planck length.
Whatever exists at the smallest scales of the subatomic world, and however these things behave, scientists say they must make sense of it all before they can possibly comprehend the cosmos above, human behavior, and what might have existed before the Big Bang. It's a mind-boggling amount of information tucked inside an unimaginably small space of our microscopic universe.